I hope everyone's doing well. I am Mr. Rich. Thank you for joining me for this video. We are looking here at a comparison of organic acid strengths of these three organic compounds, everything being derived from your basic acetic acid, CH3C double bond OH. You can see a common group showing up in all of these, and that group here is the carboxyl group, and you know that to be the COOH. Carboxyl group. And the only difference that lies here with regards to these compounds is this item right here, which I am boxing for you. That is the only difference. When you look at this compound, you're seeing there's a methyl group attached to your carboxyl group. When you're looking over here, you have a carbon with 3 methyl groups attached. These 3 methyl groups are attached to a carboxyl group. Here you have 3 fluorine atoms attached to the carboxyl group. But which of these is the strongest, which is the weakest, and why is that the case? Let's look at everything in a generalized manner. If you were to do a dissociation over here, what do you have? You have a CH3, C double bond, O minus plus H plus. When you're looking over here at this compound, you know we're looking at carboxyl group, so let's erase this. When you're looking over here, what you have is this. You have a C and then the 3 methyl groups, and then you have a C double bond, O minus plus H plus, and lastly, when you're looking over here, you have obviously a carboxylate. These are called carboxylate groups. These O minus are called carboxylates, but that's what you have. You have to identify which one is the strongest, which is the weakest organic acid, and you can focus in right over here on these carboxylate anions which are being developed. What is the stability of these, and how do those attachments or these atoms attached to your carbon affect that carboxylate anion? When you look at any of these carboxylate groups in a very general manner, this is what you're looking at. You have that, but it has a resonance structure which can develop, and you can do this. That's what it is in terms of resonance. You have a, but in general you can say what you really have is this. You have that minus being spread out evenly across the entire functional group versus only on an oxygen. These resonance groups don't represent true structures. The reality lies somewhere in between, and that reality is this, what I'm showing you for here in a larger format. Your carboxylate anion would look something like this, with a negative charge spread out evenly over these 3 atoms versus only 1 atom. So keep this in mind, because this is what we're looking at in terms of stabilizing for our acid comparison or strength determination. So when we are looking at the carboxylate anion, which of these groups here helps to stabilize this? What does the negative charge here represent? It represents an excess of charge. How can we deal with that excess of charge and remove it away from this so we can spread it out over the entire molecule? And the best way to do that is to have electron withdrawing groups or electronegative groups. You know, in terms of electronegativity, if you're looking at hydrogen and carbon and fluorine, if you have carbon, hydrogen and fluorine, in terms of electronegativity, you can say hydrogen and carbon are relatively equal, but they're definitely much less than fluorine. This has a fluorine, this has methyl groups, this has hydrogen groups. Methyl groups are electron donating more so than hydrogen. They're more electropositive. If I were to bring in this electronegativity trend over here, the methyl group, then we're really looking at hydrogen and carbon being relatively equal but much less in fluorine. But even the CH3 will be even further less than hydrogen and carbon because it's electron donating, it's electropositive. This right here is electropositive group, this right here is electronegative atoms, the fluorine. This right here is relatively neutral because you have hydrogen. Because of the presence of these electronegative atoms, the fluorine, you can help pull this negative charge away and into this part of the molecule, making this relatively more stable, and because of that you can spread this negative charge over the entire molecule, and this would have a more stable anion, hence it would lead to a stronger acid. This right here would be your strongest acid, and we'll write SA. This right here is electropositive groups, your methyl group, CH3, 3 of those, CH3, CH3, CH3 attached to a carbon, and you know carbon is relatively equal in terms of electronegativity with regards to hydrogen, but this right here would be the least acidic because you are now, because of these electron donating atoms and or groups, actually sending more charge into your carboxylate. Therefore you're not evenly spreading it out, you're actually making this negative more negative because you are, with the presence of the CH3 groups, sending more charge into your carboxylate anion, hence therefore destabilizing. So this is least acidic. That's the strongest in terms of acidity. This is least. This will be right here in between, because these hydrogen atoms are not doing much with regards to pulling effect, but they're not doing much with regards to the inclusive effect. They're not either withdrawing, they're not adding to this negative charge, they're keeping relatively the same. So this right here will be medium acidity. So if you're going to rank these from 1, 2 and 3, this is 3 in terms of most acidity, this here is 1 in terms of least acidity, this right here is 2 in terms of moderate acidity. So keep that in mind. Everything coming along with the carboxylate anion, this negative, are we pulling it away by means of electronegative atoms, or are we adding to it by means of electropositive groups? If we are adding to it, we're bringing in more charge, and therefore we're kind of destabilizing this carboxylate anion, leading to a weaker acid. If you're pulling away that negative and spreading it over the entire molecule, we're stabilizing it and leading to having us a stronger acid. If we're somewhere in between, then we're somewhere in between. This right here is your most acidic compound, this right here is next, and this right here is your least. That will be trifluoroacetic acid, this right here will be acetic acid. And if you want to call this something, you can call it this. We have carbon, we have a carboxylate group, and then we have carbon here, carbon here, carbon here. We have 1, 2, 3. Being the longest chain in terms of carbons, we can call this 2,2-dimethyl, because we have 2 methyl groups, which are your CH3 groups, propanoic acid, and that's what it will be. I won't have to stress this too much out because it's not organic chemistry lesson, but this right here is 2,2-dimethyl propanoic acid, because it has a propane group with a carboxyl, and you have 2 methyl groups attached to your second carbon, 2,2-dimethyl propanoic acid, and that's what it is, and we'll leave it to that. And that will be the end of this video. Thank you.